Hello. And I can't say good morning because my understanding is we've got some folks across several different time zones, but my name is Jim Swain. I'm an applications consultant with Synergist Technologies. Looking at the screen here, realize just how bare this introduction screen is, so we'll move on fairly quickly. What we're going to be doing today is, there we go, sorry, a little bit of technical glitch on my end. We're going to take a quick look at the role of simulation in general in the design process, and then dive a little specifically into FEA, a little farther into where Nastran In-CAD comes into play in that, and look specifically at thermal analysis and what Nastran In-CAD brings to us inventor users along those lines, and then a bit of a wrap-up. So that's the general plot I'm looking to follow during the course of the next hour. So this slide's probably not new to many of you. It's taking a look at the overall process that a product gets developed, brought to market, and sold. You can argue at which step this begins. Does it really begin at sales and marketing? Does it end at sales and marketing? Or does it just keep going around? And I think that's probably my opinion on it. And really where the role of simulation is to try and bring that confidence in the product, in my mind, bring that confidence in the product earlier to the game so that you're up at that beginning, up in that sales and marketing, and validating that your approach is the best approach for you in terms of performance, in terms of economy, and then it's going to meet the customer's needs. And then moving on from there. Too often, simulation gets stuck down in the test and validation stage only, and by then, it can be a little bit too late. So, another slide that you may be familiar with here is what do we actually use the simulation for? Well, predict performance for planned use. That's always something to be careful of, what's actually planned versus what's going to happen when it gets out in the real world. Possibly predict what might go wrong with predictable abuse. Again, be careful with that because it's hard to predict what actually is going to happen, but you can use your experience to develop a good feel for that and then apply that knowledge to your product design. At the other end of the spectrum, take a look at what's gone wrong on current design, previous designs, and use simulations tool to try and understand why that took place. What was the root cause based on what happened in the field and what you see on the product? Take an existing design and start to work to optimize it, maybe for performance, safety, or cost, weight, efficiency. And then develop new and innovative concepts. And this is one that I really, really would like to see more people adopt. Start using simulation earlier in the process so you can pick and choose between different design routes, different concepts, and try and decide which is the best one to put, or ones to put your efforts into, and use simulation to help you come to that decision. And then as you go through the design, use simulation to help narrow things down, optimize your design as you're going into it, rather than sticking simulation just at the tail end when you're trying to make sure that it's going to work. Doesn't mean that's not a valid role for simulation there, but that's not necessarily the best way to get a good bang for your buck. Another way of looking at it is the classic chart of cost versus how much effect you can actually have on the design. And I would almost want to push that gray arrow a little farther to the left if possible. Have it bridge that gap between conceptualization and design engineering, or all the way into conceptualization, where you're taking a concept and seeing whether it has a chance of working or not. And that's at the very low cost end of things. So that's before you've had much work put into developing the design, starting to make production ready, even pre-production ready designs, but still something that's manufacturable and hitting at the concept stage. Are you going down the right route? Is this the best route to go? Can you prove that? All right, let's take a look through simulation. All right, now moving further down, as far as simulation goes, for today we're talking about finite element analysis. So here's a short little description of it. I borrowed this from Wikipedia, as I mentioned here at the bottom. And in reality, if you can read this entire description and make perfect sense of this, this seminar might not be the best use of your time because you're going to be ahead of me. Yes, I understand the concepts here, but this is a mouthful. So let's try and dial that back a notch. So FEA, finite element analysis. And really, it's the idea of taking a complex, continuous geometry. In this case, you're looking at a cross-section of a part that we'll be looking at a little bit later in more detail, and mapping that, simulating that by a series of small elements, hence the name finite element, and then running your analysis on that. You apply loads, and that's in parentheses because a lot of us will think of a load as being a force or a pressure, but loads could also be a temperature, an electromagnetic load, things along those lines. Excuse me. And also constraints. So something's going to resist that force being pushed onto it. Solve for the desired results, meaning, am I trying to see if this is a piece that's going to fatigue? Am I trying to see if this is a piece that's going to buckle? Is this a piece that's just going to flat out fail in tension? Is it going to be too hot? Is it going to expand too much? That's what I mean by solve for the desired results. And as I said, the results could be stresses, deflections, vibrations. Is this a natural frequency that I really don't want to have the design fall in? And is buckling going to come into play? Am I going to be compressive loading this and have it fail due to something letting go in that way? The FEA process itself is pretty well outlined here. You create your geometry, assign material properties to it, create a mesh on that design. On that mesh, you apply your loads and your constraints. Here, the classic physical forces. And then take a look at your results. And my guess is those are stress results, looking at how it was constrained and how it was loaded. That's a pretty good bet. And then, really the important thing there is use that information to go back and improve your design. Now, I made the pitch earlier on that you want to do this early in the design process, maybe before you decide what kind of fillets you're going to use, especially around, let's see if this will come through, on the outside edge. Maybe just do this even before that. Is this even the right kind of latch? Do you want to have this as an overlatch piece, and so on. The other thing I want to point out is one of the traditional time-consuming steps in simulation is taking a piece of production-ready CAD geometry, and I'm assuming we're working on 3D solids here, so it's not a case of having to build the solid from scratch. It's take the time that's required to take that production-ready CAD geometry and make it into something that's more simulation-ready, where you're not worried about the individual microscopic details unless they're an area that's causing problems. So if you have small fillets or chamfers, small surfaces and such that are needed for production purposes, but really aren't bearing the load, whatever kind of load it is, a lot of times the analyst has to spend a fair amount of time cleaning up the geometry. Now, SimStudio is a nice package developed from the Fusion product that speeds that up. But you move the simulation early in the process and you build simulation-ready geometry in the beginning before you worry about making it production-ready, that you save all of that time. You save the time making it production-ready and you save the time cleaning it up, and you're back to evaluating which concept from the simulation geometries is the one that you want to proceed with and invest the time accordingly. So there's a pitch. As folks that know me know, I get a lot of exercise standing on and off of soapboxes. That was me climbing on a soapbox there. Do the simulation early and often, and do it with geometry before you spend the time to make it production-ready geometry. All right, so moving on. For those of you that are new to simulation, I'm going to make a little bit of a pitch here. There's a great series of videos out on YouTube done by the Autodesk simulation folks. They have a channel out there, SimTV, and they've taken an approach on some introductory videos that I love. It's the superhero simulations. Now, I've been enjoying the recent batch of movies that have come out, the Marvel, Iron Man ones, Thor, the Avengers, those movies. I've been just getting a kick out of nice escape cinema. Well, they've taken this to the next level and have done things like the one that's on Nastran In-CAD takes a look at a linear elastic analysis of Thor's hammer. There's one that does a CFD study of the Batmobile. Another one does a CFD study of a Batarang and how that might look going through the airflow. So they're fairly short. It's about a 5-minute video for this one. I'm not going to show it here. But it's a nice light introduction to a concept that's also kind of fun. So if nothing else, if you have kids that you think might be interested in going into technology, yeah, a lot of this might go over their head, but hey, this is some of the stuff that you might be working on and get them interested in too. Okay, once again, I'll get off the soapbox and move on. So, talking more specifically about Nastran. So, Nastran In-CAD is a general purpose finite element analysis tool that's embedded in your CAD system. The phrase your CAD system, I'm running it today in Inventor. It's also available for SolidWorks. It's embedded in the software, so those of us coming from Inventor Professional are familiar with the stress analysis and the dynamic analysis available here. You're going to see this right on the same panel on the ribbon. It's using the Inventor as the preprocessor, postprocessor for Nastran as the solver. So Autodesk, just about 2 years ago now, acquired Nastran Solver Company. Of course, the name escapes me. I don't have it written down on my cheat sheet in front of me, so my mistake there. But it's a well-established Nastran solver capable of a wide range of simulation capabilities. For those of you that are in industries that have a history with Nastran, this is great because you now have a solver that you can directly compare to your existing solvers and take that part of the unknowns out of the equation. You're working with an Nastran solver. What does it give us? Well, with Inventor Professional in the past, we've had that linear statics you see in the upper left corner. We've had normal modes, as you see coming a couple more over to the right on that top row. But we've been missing any type of heat analysis. We were missing any type of working with non-elastic materials, non-linear materials. We haven't been able to do buckling. We haven't been able to look at composites. We've got very limited contacts as far as assemblies go as well. This takes us out of that limitations. We can work with advanced material models, nonlinear analysis, including transient heat, transient stress, frequency responses, impact testing, hyperelastic materials, things that we couldn't address before in that Inventor Professional model. This is all still within the Inventor or SolidWorks product. So, getting quickly to the meat of today's discussion, I'm going to talk about thermal analysis in particular. Again, that's one that we haven't had in the Inventor Professional up to date, and one that's been very high on the wish list that folks have wanted to be able to get to. Types of thermal analysis you might run into here. You can see it's a friction loading of a disc brake setup. I'm not going to do that today, but it's certainly within the capability of the software. Here we've got a piece of production equipment. This is actually an Inventor model of a manufacturing line for yogurt products. So it's a packaging line that's going to take the bulk yogurt and put it into the cups and package the cups. And if you think about it from a thermal point of view, that can be pretty important because you need to keep your product in a certain temperature range. Yet at the same time, you need to elevate the temperature of the machinery periodically as you have to go and clean it, whether you're switching a product from one flavor to another one, or it's just a end of shift cleaning or periodic cleaning dictated by the manufacturing process. So a little bit of a closer look. You see, we're going to be starting at the assembly level and then diving deeper into the thermal analysis from there. So with that, I will kick over to Inventor. And here's that sub-assembly that I just had on the screen a moment ago. And you can see we've got a lot of mechanism going on here with the overall setting. I've already dived down into a level of detail. It's got a section view cut out, as you saw in that previous slide. Now, Nastran In-CAD is available both at the part design and at the assembly design level. I'll give you a look at it here at the assembly, but I am going to kick over to the part design then for the rest of today's discussion. Please bear in mind, if you would like to see more in-depth presentation of the product, contact your account representative and we can set something up. We're keeping today at a little bit of a higher level, an introduction to some of the thermal possibilities, thermal analysis possibilities in the software, and also trying to stay within the time frame of the 1 hour. So right now it's loading up the information, and I should have my browser come back in just a moment. This is one of those dreaded times when you're doing a webinar where you just try and think to yourself, how are you going to occupy everybody's attention while waiting for the screen to refresh itself? There you can see it sinking in. Every now and then you click on the mouse button in the hope. It's like hitting the elevator button when you're waiting for an elevator and you hit it 3 or 4 times. You know it doesn't make any difference how fast the elevator gets there, but it just makes you feel better. And at this point, I'm saying some very nasty things about Citrix under my breath because this is unfortunately, it's a different response time when you throw the webinar software on top. Okay, so it's going to be a little bit bulky today. Interesting. I hadn't expected to kick out that. Could be a little bit interesting. You may see how I react to a, there we go, thank you. Always compliment the software when it does what you were asking it to do. It responds better that way. So, here you can see over on the left-hand side, we've got various bits of information. We've got some materials brought into the model. They're not currently assigned anything. That's why you saw that warning message up there saying that, hey, if you're going to proceed, you're going to need to do some more work. Mesh needs to be updated. And here, down here in the lower part of the browser, you can see I've got a pair of physical properties with materials assigned to. In this case, a stainless steel for the sleeve and a plastic material for the piston. Up towards the top, the mesh saying it needs to be updated. A thermal analysis has been kind of set up on this. As I said, I'm not going to go further on this particular one. Just want to give you a bit of a heads up on this. And I wanted to let you know that at this stage, since I am working at an assembly level, it would be appropriate to go and add contacts between the various pieces to indicate whether a part is going to be sliding relative to another piece, or if they're both welded together, even though they're welded should be in air quotes there, if they're stuck in the same relative position to each other, and so on. Is it a bonded contact? Is it a sliding, no separation contact, and so on? So you have the ability to work a lot further than you can with the Inventor Professional. Step away from this one and go down to the sleeve. So here we are in a single part. And again, I'll go back to the environment. You can see I've got a little bit of a different look here because I am looking at a part rather than an assembly. And again, fire up Nastran. And this piece has already been meshed. We don't have to wait. A lot of times, and I'm doing a little bit of it here, you'll have a demonstration during a webinar that's reminiscent of the old cooking shows where you put the raw cake batter in the pan and the top shelf, break for commercial, and out comes the finished cake on the bottom right after the commercial, ignoring the 45 minutes of cooking time that actually was required to make that cake. Here I have something that's already been meshed. The material properties came over from the CAD system, but let me just show you what type of things you can be working with there. So it recognized that I was going with a material from the Inventor Material Library and pulled the stainless steel from here. That material is given a specific name. It's got some basic properties, various requirements from wow, having trouble with words right now, that are needed for the types of analysis that you're going to do. It's been assigned to it. From there, we would be going and adding constraints and loads. So the workflow, classic ribbon workflow, we would start at the left and work our way to the right. This is an existing analysis. The materials have been brought over already. See, at this point, again, something that's always been a bit of a challenge with the Inventor is being able to allow for simplification of the model, where you can say that you're going to do, let's say, a fixed constraint. That one's fairly straightforward. I could do a fixed constraint on a surface and pick another surface to simulate a bolted connection, if that was appropriate here. Or, you can see it's already labeled here, but I'll go ahead and recreate it. I could also do a symmetry constraint. So maybe symmetry in this case about the XY plane, and you can see what it says is it's still allowed to move in X, still allowed to move in Y, so it's still allowed to shift along this plane or away from the plane, but it's not allowed to come towards me as far as this surface is concerned. It's not allowed to rotate away. So you can go and add those capabilities to the, oh, sorry, I bumped my mouse there, to the piece. You can see that apply the constraints to the system. So there's where I had previously added the symmetry in this case. Go ahead, there's no context needed here. This is already meshed, and I'm going to just keep moving through this. You'll see some messages come up during the analysis indicating that I might want to come back in the future and explore tweaking my mesh a little bit. You'll see some messages come up because I am going to run the analysis. This one takes about 90 seconds or so, at least it did last night. We'll see how life goes today. Things that you can do, set up an overall meshing properties, how much it's allowed to change. It goes from one region to another and so on. But let me just go and hit the run here. Oh, sorry, I forgot to talk about the loads. Yes, I know, it was canceled. So for the loads, I haven't done anything yet. I got a little bit ahead of myself there. So stop clicking for a moment and let Inventor catch up with me. Again, saying nasty things about Citrix under my breath. Actually, that one was my fault for canceling the meshing. That was a self-inflicted wound there. But what I'm going to do from a loading point of view is I'm going to add some thermal loads. I'm going to be adding, as soon as I get an opportunity with the software, and not responding, I'll be adding an initial condition. So I'll give it a starting temperature. And then I'm going to give it a final temperature and have it a convection load to go ahead and take a look and see how much time it's going to take to get there. So Once again, we got to put up with me having clicked a couple of times too often on the screen. And actually, it would probably make my life a little bit. Yeah. So that was the software guy yelling at me for being stupid. So I will go and add a load here. In this case, what I'm going to add is initial condition. And set that initial condition. Notice how it's going to be a temperature right off the bat. And it's in degrees Kelvin. I'll set it roughly a room temperature. And then I'll come back and also add a body temperature. And this is going to be the elevated temperature. This is going to be the wash temperature coming into play. So I've added those two to the system. Hit that one more time just to make sure that I've got them in there. Oh, actually, yeah, looks like I might have one more time just to be sure. Condition, temperature, room temperature. All set there. Okay. There we go. Notice how it's showing up. They didn't show up before, and I'll try and figure that one after, but I'm going to put it down to Murphy. And me just being a little bit of a rush since I'm technically on the recording. The light bulb went off. What I was doing wrong. So now it's load 9. No, I'm doing something slightly wrong. That's the one I want. I think the one I want. Let me just do a quick check on there. Yep. So I'll drag that up there and apply it instead of me typing. So I've got a pair of loads, 2 different temperatures. Go ahead and run the analysis. Notice up here at the top, this is a thermal expansion load. The linear static. If you're not familiar with the linear just implies that if I have twice the heat difference, the expansion is going to be twice as much. It's a nice straight line. It's a ratio between how much you apply as far as the loading and what your result is. Nonlinear would be, no, it's not just a single straight line relationship between the two. While I'm trying to kill a little bit of time while the analysis is actually running, I'll point out also that one of the things that with the Inventor Professional, we've been limited to linear elastic, which means that pushing on something twice as hard gives you twice the deflection, twice the stresses. That's good for very small displacements. It's where that assumption works best. But what we run into too often in the real world is you can't get away with just that basic assumption. So there you can see that the volume meshing is going on now. Overall progress, so we're a little bit of the ways into it. As I said, when I ran this yesterday, this was about a 90-second process. I'm feeling a little nervous right now just because the process is running a little slower than my dress rehearsal. But that seems to be the way today is going. So we'll give that a few more moments to keep going. There is a cancel button if I do decide to panic. All right, so this is a result of my problems from earlier for me going and messing things up. So while in a class or in a real application, I would go and spend time to redo that mesh and analyze what's going on. For today, I'm going to move on and do pretty much the same thing. I'll do a couple of analysis here on the other part. This is the plastic part. Again, I'll go into the Nastran environment, and it's loading up the analysis files here. That's the part that takes this initial time as you come into to play with it. So here, this analysis again, it's a linear static. It's already got constraints loaded. Already has the material loaded. And looking to see whether we've got loads already applied. No. So let's go and grab, let's try it one more time in front of an audience. Go and apply a couple of loads. We'll go with, again, a initial condition of roughly room temperature. And we'll keep that one there. And then we'll apply the second load of telling it has to go up to this, and we'll see what the thermal expansion is here. And let's see, anything else I'm going to regret doing? Now we'll go ahead and hit run. And it's giving me a warning, Nastran In-CAD. That's true, I didn't set up anything for load case check. All right, how to do wonderful in front of an audience. Okay. So what I would have been getting from this analysis, I'll probably come back to it again, we still have time in this session, is try to stop shooting myself in the foot. Let's take a look at another type of analysis that would be coming into play in this. And if you remember the initial scenario, we were talking about something that was going to be used as a food processing, so it was going to have to be cleaned. Once it's cleaned, it would need to get back to its normal operating temperature, so an elevated cleaning cycle and temperature, and then the machine can't be used until the equipment's back down at its regular operating state. So here, what's going on is a convection load's been set up. And this is a nonlinear transient where, let me pull that over so you can see a little better, nonlinear transient heat transfer. So how fast is this thing changing over time? How fast is it cooling down? So what we've got is not only setting up material properties, putting in loads. In this case, we've got a convection load that is a temperature dependent, where initially the convection takes place at a higher temperature, so we've got a higher rate, and then we're simplifying how this behavior is by making a simple piecewise linear. Couple of different pieces. You can make this as complex as you wish. So I'm canceling out of that edit. I will also go and apply an initial condition here, because it's got to start at something. And we'll start at that elevated temperature. As far as the time steps go, I'm going to do 60 seconds with a time step of 60. I'm sorry, 360 seconds altogether, but the time steps are 60 seconds. And it's 60 time steps, hence the 3600. And this one does run a little bit longer than the other one, but since the other one didn't run, I've got a little bit of time that I can afford to let that go. So here it's building the Nastran file. It's taking the information from Inventor, kicking it out. And I mentioned earlier that it's going to be doing some checking. And what you saw briefly in red there were some elements in there that it's letting me know that they're pushing the limits of what are considered nicely shaped elements. So that might be something I want to go back and check on in the future. And this output log that you saw there for a little bit, available for me to inspect and decide whether it's something that I need to worry about, or is it just a warning that I can ignore, because it really doesn't come into play with my analysis. As the temperatures are moving, I can ask for a display of that. So you can see the core is still holding its heat pretty well, and the outer skin is coming down a bit. And also take a look at a plot of where things are at this moment. So we're not through the end of the analysis. It's only about 600 seconds into it. But you can see how the trends are going. And this is a maximum temperature versus time. So it's holding, and then starting to drop. And let's see, how far are we on this? Yeah, about a third of the way, a little less than a third of the way through the analysis. So it's running very quickly. It's the actual amount of time is not very long for this analysis. This machine that I'm running on is my laptop machine. It's a Dell Precision. It's an older one. It's an M6400. It has 16 gigabytes of RAM. So it's not the latest and greatest machine. It's not the biggest amount of RAM you could get. It's only a twin core, dual core. I enjoy having this on a machine with a few more cores available to me because I can take more advantage of them here than I can in the inventor world. Let's see, anything else worth noting at this point? Again, you can see how the temperatures are dropping as you would expect. Let's just take a look at that plot again, see what's going on. So now the curve is starting to flatten out a bit. We got past that 600 mark from before. And I'll start to see this taper off a bit more as the temperatures come down. What I'm not showing today is how I could run an analysis where I would take a look at how the relative size of this piston and the relative size of that sleeve that it fits in vary with the temperature as well, because we're looking at two different materials, a plastic and a steel, stainless steel. So as that goes up in temperature, am I going to go from a minimal clearance needed for the piece of equipment to operate, this being a food industry processing equipment? It's intentionally designed to not use O-rings in the product path, so you don't have anything that could hold material there and possibly get into a sanitary issue. So that relative clearance is important, both at the operating temperature, but are things going to jam up as the temperature changes? What happens if you've got a change in product that now might need to be packaged at an elevated or refrigerated temperature? And we go and take a look at those different scenarios. You might find that here this plunger has a small threaded portion up towards the top and a screws onto a rod that's coming down. Well, maybe to cool this down quicker so that you're not wasting time waiting for this cool, you want to run that threaded rod down further into the piece, or even just run a portion into it there as a heat sink. So while I was babbling on there, the analysis finished. Let's take a look at what the final version of that plot does. And here you can see you've got that initial steep part of the curve, a flattened, nice linear section there, and then as temperature on the core gets closer and closer to room temperature, less and less heat comes out, so the rate of cooling slows down. It's always good to do a sanity check. In this case, I agree with the type of results that we're seeing there. Now this was a thermal analysis, but I could still take a look at that and also see what I want from a heat flow and so on. These temperatures would then be available to go back into another analysis where I'd be taking a look at, based on the temperatures, what's the expansion, based on the expansion and the fit with the other pieces, what's the contact. In fact, it's in a video that's available. We'll see how timing goes. Maybe I'll pop that up there at the end and let that run for about a 10-minute video. I didn't want to do that as a live piece. So let me pause here for a moment and recap what I talked about today. Talked about how Nastran In-CAD brings more capability into the Inventor environment that we haven't had in the past. It directly reads my CAD geometry, and again, I'm saying Inventor. It is available for SolidWorks as well. It's bringing material properties over from the model. I can reassign to other properties here at this level if I wish. I can tweak those properties if I've got more information available here. I can add to the material property. I add my constraints and my loads. Similar to what I've been used to in the past with Inventor Professional, with a lot more capability, both on the constraints with the symmetry availability, as well as the loads with thermal loads, transient loads, and also the availability of other styles of contacts. From there, work my way across left to right, mesh the design, and go ahead and do the run. And we saw that for this design, which was, what, about 20,000 elements, about 32,000, almost 32,500 nodes. So that was a fairly quick analysis that it ran through 60 time steps for. So it is a piece of software that can be employed early in the design process and used for comparing concepts quickly, easily, effectively before you get too far into your design. With that, Ashley, are there any questions at this point?
I don't have any questions as of right now. Like I said, you can type your question into the window pane, or I can unmute you if you use the raise the hand feature. I'm not seeing any.
Okay. Still see people logged in, so folks might be enjoying their morning coffee. I know I would be. But, well, let me go back to my PowerPoint just for the wrap-up.
Looks like we do have a question.
All right.
Let's see. What is the difference between the part and model trees?
So I'm in the Nastran environment right now. The model tree is where I do all my setup. So I'm applying my physical properties, which are the materials in this case. I'm applying my loads and my constraints, getting my meshing set, and so on. That's that Nastran model tree. I also had the Nastran output, and this is what was going on. As I was mentioning, I had some elements that the shapes might want to be tweaked a bit if they're falling in an area of interest. But this is what's keeping track of the actual analysis. And then I can also take a look at the Nastran deck that was written when the analysis kicked out. I can look at this also using file, drawing a blank, something like Notepad, WordPad, those types of programs. So this is basically a text file. But the ability to go in here, there are flags and settings that an experienced Nastran user may want to go in and make some adjustments to. They have done in the past. You have the ability to do it here now to the actual Nastran file. So that's what this part of the browser is for. So for typical design work, you're going to spend most of your life here in this Nastran model tree. Now, if I were to leave the Nastran environment, then I'd be back at my regular Inventor modeling tree, whether I'm at a part level or at an assembly level. So hopefully that answers your question. If not, maybe we can take it offline and have further discussion. Any other questions? And also, please let me know if that didn't answer your question.
Not seeing any other questions at this time, and we have a response that did answer his question.
All right, so either I successfully answered or the person was bored with me talking. Either one's legitimate. Okay. Got a little bit of feedback there. Was that somebody being unmuted or
That was
anything else?
nice. That was me. I will mute myself again, and you can continue.
So, all right. So let me just go back over to my PowerPoint and just see what I have as far as wrap-up goes, and then we can come on back. Honestly, what I'll do is for the remainder of time, once we go through the wrap-up, I'll go back and you get a chance to watch me try and fix where I shot myself in the foot earlier. I figure you deserve that. So, from a simulation point of view, Nastran's falling over in the structural mechanics end of things. Simulation Mechanical's been on the market for a while. This is Nastran's much newer. What's not listed here is Inventor Professional with its built-in finite element analysis capabilities. Also the dynamic analysis capabilities in there. Nastran would also come over here for just a straight thermal analysis, as well as Simulation Mechanical applies in that realm as well. So just want to give a little bit of a feel for what else is out there in the Autodesk world. And the overall simulation philosophy is the products that Autodesk acquires are typically available for a range of CAD products, and they maintain that. Again, I've been working up here through the Inventor environment, but you're not limited just to Inventor. Nastran In-CAD is available for the SolidWorks platform as well. A lot of integrated solutions across the different realms. And really what I want to point out here is that there are specific solution tools available for specific challenges that you may run into. And there's also various licensing models to help you be able to reach your goals, be able to afford to go there. So I guess that's probably the biggest reason I included this slide. It's got some pretty graphics on it. Encourage you to go out and take a look on YouTube and take a look at the Simulation TV. That's one of the places that you can get a wealth of information for what's available from Autodesk out there. There's also the discussion forums for the simulation. And certainly we're available at Synergist as a resource as well. And I think that's the last slide that I have. Oh no, I apologize, I forgot I threw this one in. I'm going to make a pitch for Autodesk University. Coming up the week after Thanksgiving, so that first week of December from Tuesday through Thursday, out at the Venetian Casino in Las Vegas. And that, for some people, is a challenge there, though I know in the last few years that I've been going, I have yet to do any more than walk through the casino floor because there's too many sessions that I'd like to go to and attend. Yeah, I guess that says something about me as well. But there's a full simulation track available out there at Autodesk University if you're looking to learn more as either an experienced user or someone new coming into the game. So please consider signing up for Autodesk University. If you do, give me a shout. I will be out there as well doing a talk on taking from art to part, what you can do in Inventor with plastic part design. Without going for deep into simulation, I'm staying with the basic Inventor tools, just a touch beyond. So with that, that's the end of my formal presentation. As I said, I'll kick on back over to Nastran and I'll poke around a little bit and fix where I shot myself in the foot. And you're welcome to ask some more questions. If anything comes up in the next few minutes, please let me know, Ashley, and be glad to answer what I can. Other than that, you're welcome to watch and otherwise enjoy the rest of your day. So thank you. So for anyone that's still listening, I'm going to start with the classic close without saving and reopening. It's a great way to remove sins from your CAD model. And please, Ashley, let me know if anything else comes up as far as questions or folks raising their hand. For those of you still listening, what we're doing at this point with going into the Nastran is loading up the Sage files. So all the information is written out to external files tied to this inventor part file. So here you can see it's already been meshed, 37,000 nodes, elements roughly, almost 63,000 nodes. So it's a fairly tight mesh on here. Currently doesn't have any loads, so I would go and I can just go and drag those existing predefined ones up or create them on the fly. There's the room temperature one. If I edit that, you can see that that is nothing more than an initial condition at room temperature. Or, as I said, I can go and apply a body load. Sorry, body temperature, wrong word. So I came in with load 5. Yes, I could have dragged one out from down below. Fingers crossed, wishing it to run. And this is the one that took about 90 seconds in the past. Just a straight linear static. Yeah, it's running fine this time. You will see warnings about a series of elements that are not nicely shaped triangles. Also, there was a piece of information data that was essentially a 0, but it's not needed for this thermal analysis. It was the material property. So it was just some extra values in there that I really don't care about for this analysis. The only reason I'd change it would be just to get rid of an annoying red piece of text on the screen. Those interior angles, those are the warnings I was talking about. Again, if they were looking like they were coming in an area that was the particular concern, I would go back and figure out which those specific elements were and look to change the meshing in that area.
Okay, it does look like we do have a question.
All right.
In the linear statics module, what other results are available besides the, von Mises?
All right, let me see if I can read that question on screen because I unfortunately didn't hear you. Oh, von Mises. In linear statics module, what other results are available besides von Mises? All right, let me go over to the results. And you can see here what I've done is I just clicked on the results tab there. So there's a pretty good selection to choose from. As you can see, we do have the principal stresses besides just the von Mises, max shear, minimum shear principles, looking at displacements. And if you attend one of my classes, you're going to hear this preached at you. Always look at displacements first, because it's how you check to see whether or not you have things locked in place right, or did this 1 ounce of force send it into orbit around the moon. You know, a quick sanity check there. But there's a wide range of options available to you. Many of them aren't appropriate for what I did here with it just being a heat loading. So that's why I just go to the displacement. In this case, I'll stay with total, but you could take a look at the different components of that displacement. And you can work your way through, that's my contour options, taking a look at displacement, my deformation. I want to look at the displacement. I want to multiply it by 10%. Yep, I think I'm reading that right. 24 levels. Let's see what that looks like. So my displacement, there we go. Here you can see I've got a minimum displacement of about, 3/100 of an inch over there, maximum about, just about the same on the other side. Notice one's negative, one's positive. So what it's telling me is that it's shifting either side of the center bore. What I would probably be more interested in doing is not really the max min on this particular one, is take a look and say, well, right there, what's my displacement? And it's kind of hard to read on the screen. It's pretty much impossible to read on the screen from that angle. Let me swing that around a little bit. By the way, if you don't have a 3D mouse for doing stuff like this, get one. Personal comment there. So about 15 thousandths of displacement with respect to X there. If I swing it around to look at the other side with the probe, and about the same amount. So about 30 thousandths worth of expansion across the bore. And that would be the design information I'd be worried about here. So very long answer to a simple question. There's a lot that you can get in terms of your results. It's just a matter of what you want to ask for. I wanted to run that again so you get a chance to see just how fast a linear static type of analysis can run. Again, this was what, better than 60,000 nodes and almost 37,000 elements. So not a small analysis by any stretch. Okay, any other questions?
I don't see any. We can give it another minute or two.
All right. And until that minute's up or so, I would like to say thank you for your time. I hope you found this session worthwhile. If you do have questions, more detailed questions, please contact us, contact your account representative, and we can set up a further discussion, something more specific to your particular end needs, and look forward to working with you in the future.
I'm not seeing any other questions. I will be sending out a follow-up email with a link to this recording. So feel free to reply to that email with any questions and or to pass this webcast along to any fellow colleagues. Thank you all so much for your time today. Have a great rest of the week.